Okay, thank you very much, David. And first of all, as the last speaker, I'd like to thank on behalf of all of us to the organizers for organizing such an interesting conference and in this beautiful place. Yeah. Oh, okay. And of course, thank you also for giving me the opportunity to talk about this exciting work. So I'll discuss Landau singularities and asymptotic expansions in 2-to-2 scattering. It will be a while until we see Landau singularities, but believe me, they are important. So this is based on collaboration with Franz Herzog, Stephen Jones, Yao Ma, who is in the audience here, and Johannes Schlenk. And these are the two papers that I'll mainly focus on. In fact, the main topic of the talk, the second part of it at least, would be dedicated to dissecting polytopes, Landau singularities, and asymptotic expansion, as the title says. So I hope we'll get there in time to explain this in sufficient detail. So, but I know that most of you have not worked with method of regions. I mean, this method exists already for many years, and nevertheless, this is maybe a slightly different community that has been working in this. So I thought it is really important to give some pedestrian introduction and explain what it is all about. So first of all, the method of regions is a general method to perform asymptotic expansions of Feynman integrals. Why is this important? First of all, this is a very useful computational tool. So we saw in Young's talk, for example, that Feynman integrals, even at 2 loops, sometimes are incredibly difficult, despite all the progress that has been made. And one thing we can always do is expand. Okay, and that's the first reason to do that. But it's by far not the only reason to do that, because one of the most interesting things about scattering amplitudes are the special kinematic limits, where things are singular. And you saw also that in Young's talk, in the context of the space-like splitting, where there is factorization violation and so on. This is guaranteed to continue to be an important aspect. And it is precisely by the method of regions that we understand special kinematic limits. Now, the method of regions was originally formulated in momentum space, and we will review that momentum space approach briefly in the beginning. Momentum space is extremely important because the regions that are associated with the behavior of the dominant loop momenta that contribute in the particular kinematic limit, they give intuition for what are the important contributions, but not only for a given integral, but for the entire class of integrals. So basically for the amplitude and also for higher order amplitudes of the same external kinematics. And what that allows to do is to actually develop some effective field theories, such as heavy quark effective theory or soft collinear effective theory, that capture the behavior in that limit more generally. So these are just examples. Now, in parameter space, there is other advantages, and it is extremely useful to be able to go between these different representations and take full advantage of the possibilities that they offer. What's the main advantage in parameter space? This is the fact that singularities appear mainly as endpoint divergences. And that allows for a geometric interpretation using the Newton polytope that I will discuss. The Newton polytope, as we have seen, has many different applications. Determining the varieties where integrals are singular is one of them, but expansion by region is another, and there are various other applications of the same. For example, numerical evaluation of Feynman integrals and so on. So parametric representation is therefore very much complementary to the momentum space. Here one can formulate algorithmic methods to determine the regions. Now, fundamentally, that's the third aspect, there is a relation between regions and Landau singularities. And when we really need to understand things, we need to return to the origin of the regions in terms of the proximity to a certain Landau singularity. So that we will see in the last part of the talk. My personal motivation in studying this is twofold. First of all, I find the method of region fascinating in its own right. So I'd like to understand how it works. But the second thing is that I've been interested in kinematic limits for many years and find them fascinating. And then the method of regions is an excellent tool in order to deeply understand these limits. So an example is the Regge limit, collinear limit, and so on. Okay. Now, the outline of the talk is the following. I will start with an introduction, both in momentum space and in parameter space. This will be very brief, but I hope you'll give you a taste of what it is about. Then the new material would be in the last 2 bullet points here. First of all, I'll discuss the on-shell expansion. What is the on-shell expansion? We are taking some Feynman diagram that is finite, that corresponds to a contribution to a Green's function, where everything, all the external legs are off-shell. And then we expand it around the limit where some of the legs, the external legs, become on-shell. That's then making it relevant for massless scattering, which is usually what we are interested in collider physics. This is a way to understand the singularities. Now, so this is, in a sense, the simplest type of expansion. And it already has quite a rich structure, as I will show you, but it is the simplest one. So I'll show you that now we have quite good understanding of this, of this expansion, using a subgraph structure that I'll present, and a purely graphical region finding algorithm that shows that you can just basically look at the Feynman diagram and determine the regions based on very general graph theoretical considerations. And finally, that's basically the main point that is new in this talk is discussing hidden regions, ones that cannot be detected directly by looking at facets of the Newton polytope. And I'll give some examples for that at 3 loops. Okay, so the method of regions, let me define the aim and the strategy. So the aim is to expand the Feynman integral in some external kinematic variables. So we have a subset of variables. This is T is a subset of the variables that are getting small in the limit, while other kinematic variables remain of order 1. And then what's the main problem? The main problem is that when we start with an integral representation of the, integral representation, suppose we don't know how to perform the integral in general, that's usually the case, then the 2 operations of taking the limit and performing the integral do not commute. So the right thing to do is, of course, perform the integral and then expand. Now, what we tend to do, if we want to simplify our lives, would be to take the limit inside the integrand. Of course, we'll get a different result. The reason the result is different is that the function is non-analytic. And if we are taking the limit inside, expanding inside, we're just going to get a Taylor series at best, rather than some non-analytic behavior in the limit. So that's the problem. So what's the solution? The solution is the strategy of regions. The idea, you split the integration domain a priori into regions. In each region, you have different behavior of the integration variables with respect to the external variables in which you expand. So sometimes you'd scale them together with the external variables. Sometimes you'll keep them large when you expand. And there are many integration variables, so there is a variety of regions. And then the idea basically is that you perform the expansion in each of these regions, sum them up, and get the original integral. But here, a crucial point is that after you perform the expansion and the integral in each of these regions, you perform the integral over the entire integration domain. And that's the point where it looks a little bit fishy, might be, what's the justification? Because there is a certain radius of convergence for each of these expansions. And if we perform the integral over the entire domain, we're clearly going way beyond this radius of convergence. But that's the method, and it works in every case, okay? So clearly there is something to understand, and that's true in any representation, and I'll discuss it in momentum and in Lipomeranski representation. So basically here, what the procedure is explained here very schematically. We have the regions. In each region, we have a Taylor expansion operator acting on the integrand of this integral, and then we sum up over all the regions. Each of them, we integrate over the original domain of integration. We will use this example, and only this example, to illustrate in the introduction what I'm talking about. So imagine that you have this triangle diagram contributing to pseudo-conform factor type process. The idea is that initially P1, P1, and P2 are all off shell, and then you expand near the limit where P1 and P2 get on shell. So our set of variables that become small is P1 squared and P2 squared, and we assume that they are proportional to Q1 squared, with this lambda being the expansion parameter, which we take small. We further parameterize this P1 and P2 using light-cone coordinates as shown here. So P1 is mainly minus and P plus is mainly plus in light-cone coordinates. And now I jump to the answer. The answer is that in order to get the expansion of this integral, one needs to sum over 4 different regions. The first one is called the hard region. That means that all momentum components of the loop momentum propagating here are assumed to be large. So when I take the limit P1 squared and P2 squared to 0, I do not take K to 0 at all. And this leads to this sort of approximation. And then there are other behaviors of the loop momentum integral, one where this loop momentum is collinear to P1, one where it's collinear to P2, and one where it's soft. And then I take a different approximation in each of them. For example, in the soft, all momentum components are of order lambda, and then I neglected the K squared here and here compared to the other components. Okay, so this is precisely the starting point when we want to understand the kinematic limit corresponds to an on-shell form factor, which is an introduction to soft collinear effective theory. We are not going in this direction. Here, we would like to see what happens if we perform the integral. Let's just take these leading order results in lambda and perform the integral for each of these regions separately. And again, I emphasize that we perform the integral over the entire integration domain. What happens in the hard part is that we get infrared singularities because we threw away the P1 squared and P2 squared that were infrared regulators before. Infrared singularity. Here, in these infrared regions, where we assume that the momenta are getting small, instead we're getting ultraviolet singularities in epsilon. And that's because we neglected the K1 squared in the denominator that was protecting it in the UV. So that's because we extended the integration to the whole domain. When we sum up all the regions, as done here, we get the correct answer. And the correct answer can be computed directly in this case, and it gives this. It's finite. All these singularities, some of which are UV, some of which are RIR, cancel, and we reproduce the correct answer. And of course, this can be done then to high orders in the expansion, and for difficult integrals, this is sometimes the only way we can get analytic expressions of some sort. Now, it's more than that. Now I show the leading order in the expansion, but suppose you want to go to high orders, you can even resum the series in lambda. Here I resum the series both in the powers and in epsilon, and I get separate analytic expressions for each of the regions. Now notice the following. The hard region, where we expanded inside the integral naively, is indeed a Taylor series in P1 and P2. That's an Appel F4 that corresponds to a regular expansion. But here, these infrared regions have a non-analytic behavior as I send epsilon to 0. And that must be the case. I mean, the reason we could not just expand here is precisely the fact that the function is non-analytic in this limit and this is captured by this behavior here. So you see that the expansion by regions captures a property of the correct analytic function, and it is a natural separation. Also, if you know how to do it analytically, it captures a real feature of the expansion. Yes. What's the precise separation? Yes. Yeah, but this separation is only useful for proofs, because at the end I extend the integration region over the entire domain and just perform the integration over the entire domain. So it's called regions because it's initially set up by declaring on different regions, but eventually you don't integrate over a region, you integrate over the entire domain. You just make an approximation that's suitable in a limit. Yeah, you Taylor expand the integrand, taking into account that the integration variable also changes in a certain way. And of course, this is legitimate in a certain region and not in another. And then, once you got your approximated integrand, you perform the integration over the entire domain. That's the method. You perform them separately, typically. No, this is regions in the loop momentum integration. But there are regions in quotation marks because at the end, we don't really separate into regions. We integrate over the entire domain. The expansion is what's done separately. Okay, thanks. Okay, so yeah, I did not plan to spend too much time on this. This is an introduction to understand the context. I will quickly just recall what the status of this is. So the method of regions has no general proof. What I told you that it always works, it's just by experience it always works. However, there is a proof of the following theorem. So in 2011, Janssen has shown that given regions that satisfy certain requirements, then when you perform the integral over the entire domain and sum the regions, you'd reproduce the answer. What are the constraints? We'll not go through that in detail. Basically, you have to identify regions that are non-overlapping and together cover the entire domain, and the expansions commute, and the integrals are all regulated, and so on. There are certain mathematical conditions. Under these conditions, the result is reproduced. Now, what's the problem then? The problem is that it doesn't tell you how the regions are to be found. If you have a difficult problem, you have to go and search what the regions are. Maybe you missed one. Then you don't get the right answer. So this is precisely why I say that that has no general proof. Okay, and so precisely because of this, we now go to parameter space, because in parameter space we do have an algorithm. So that changes things completely. The algorithm is to find the regions. I'll show it in the next slide, just very briefly. But first, parameter space, just to define things. So there is the Feynman parameterization, and the Lee-Pomeranski representation will mainly be using the second for the expansion by regions. However, it is quite convenient to be able to go between different representations, and we'll be using that a little bit. These are the semantic polynomials shown here. What is very important to understand for the context of this discussion is that in Minkowski space, which is what we are interested in, these invariants st squared are generally of mixed signs. They do not have the same sign. And sometimes there is no Euclidean region from which you can continue. So generally, we just have to assume that things are of mixed signs. And that makes a lot of trouble. That's basically the key, the reason why I give this talk. Otherwise, it would have been very easy. Now, if this f vanishes, clearly there is trouble, right? But it's not severe trouble, so long as we can deform the contour into the complex plane. So the formation of alpha k, for example, in this way, by the chain rule corresponds to modifying f in this way. And we just have to make sure that we do it consistently with the I epsilon prescription. And if this derivative does not vanish, then we are fine. We can analytically continue. In cases where we can do that, there's also not going to be any problem for the expansion by regions. However, sometimes the derivatives vanish. If all the derivatives vanish, or alpha times all the times the derivative vanishes for every k, then there is a pinch, and then there is further trouble. So we will return to that later on. So let's now forget about that problem and formulate the expansion by regions in parameter space. The key advantage is that now we have an algorithm to identify all the regions. Okay, what do we do? So as before, we take a limit, well-defined limit on the external variables. They scale in a particular way. And now our integration variables are these x, Li-Pomeranski parameters. For each edge, there is a different x. And the rule would be that for each of them, we have to scale by lambda to a certain power. For a given region, these powers are defined, and that defines the so-called region vector. The region vector is the set of powers that define how to scale the edge parameters. Okay, that's basically how we would apply expansion by regions in a parameter space. We would then expand the integrand subject to the scaling of the integration variables and the external variables using a Taylor expansion and integrate over the entire domain to recover the integral. Okay, the key thing is that now there is an algorithm to determine what these region vectors are, and this corresponds specifically to a certain subset of facets of the Newton polytope. I'll not show the proof. It's quite easy to see how this corresponds to that, but I'll show an example. Yes. Not necessarily. There can be, for example, 2. In this case, yeah, they are negative, but it would be -2. So sometimes they're positive, and sometimes they're even mixed signs. But yeah. Okay. So now this is the example that I showed before in momentum space. Now we look at it in parameter space. U is simply x1 plus x2 plus x3. F is written here. You see, this example is fairly easy from the point of view that we can always go to a kinematic region where all of these are positive. So we just choose a Euclidean region, and that problem that I talked about, that F vanishes within the integration domain, is not there at all. So, of course, this is a trivial example, but it still illustrates this issue of the facets of the Newton polytope, as we can see here. So the Li-Pomeranski polynomial is written here. That's the integrand. That's the polynomial. You see that there are 6 different monomials there. And here I give you the answer. The answer is that if you look for the region vectors, you can basically do it in parameter space. Here I use the Feynman parameterization rather than Li-Pomeranski because it's easier to see. You see the blue vectors here. These blue vectors corresponds to inward pointing vectors that are normal to the facets of the Newton polytope, and each of them corresponds to a region. So the green and yellow here correspond to these collinear regions. The hard region is this one at the bottom, and the soft is the one at the back, and they are given by these region vectors. So it's very easy to do the calculation on a piece of paper. One can immediately do that. And of course, there are computer codes that do it very generally. Now, let's take an example, see what happens. So let's take this soft region and insert the region vector here, as well as the external scaling, and we see what happens to the integrand. So you see that this polynomial here that has 6 different monomials now has monomials that behave according to different powers. Only the 4 monomials here appear at leading power. They are the most divergent here. So lambda goes to 0. And if I expand, this would fly to the numerator, and I'll have only 4 monomials. Now, because these are facets of the this polytope rather than lower dimensional faces, we are guaranteed that the integral would actually give a non-zero answer. If we were looking at a face of higher codimension, so lower dimension, then this integral would vanish. But because these are facets, they do not vanish. And this is basically the intuition. And then each of these regions gives a different integrand. I'll not go through the details for lack of time, but now I would like to go through a few points of trying to understand the method. So the first step in understanding is the connection between what we have seen in momentum space and what we have seen in parameter space. And there are 4 regions. Here, it was easy to give them names and connect them. But more generally, this is not always straightforward. What I can show you is that there is a very easy thing to deduce, which is the relation between the virtuality in momentum space of the loop momentum and the scaling of the parameter. And that's easiest to derive using the Schwinger representation, where you'd see that scaling of the virtuality is precisely the reciprocal of scaling of the Schwinger parameter. The same goes, we show that the same goes for the Lipomeranski parameters, and you can immediately deduce, for example, that if we have scaling of the loop momenta like that, the virtuality scales like lambda squared, then the Lipomeranski parameter would scale like lambda to the -2. And collinear 1, -1. So that's easy to see. Sometimes, so in this case that I will be discussing, so the on-shell expansion in wide-angle scattering, that's the discussion, the direction in which I would like to take the discussion. There is really one-to-one correspondence, and if you solve it in parameter space, which is algorithmic, as we said, then we know the scaling of all the loop momenta as well. So it's very easy to translate. Just one-to-one. Hard, soft, and collinear modes, these are the only modes. Okay, second level of understanding, generalizing from this fact that, these are only hard, jet, and soft, there is the following theorem that we wrote in this paper, which was then proven by Yao in this paper following that last year. So the statement, precise statement is like that. Facet regions in the on-shell expansion in wide-angle scattering. Wide-angle scattering meaning that the angles are generic. They're not some peculiar forward limit or something like that. So for non-exceptional angles, if you want, in the on-shell expansion, there are only hard, jet, and soft modes to any loop order. And this is true to any power in the power expansion. So completely general, okay? And so these are the modes. And now there are several other properties that are essentially encoded in this diagram here. The first is that this H here represents the hard subdiagram. All the propagators that are far off shell, they are part of this. All the external momenta that remain off shell, they're connected to the hard, and the jets also connect to the hard. Now, each of these jets is separately a connected subdiagram and has one of the external light-like momenta attached to it. Finally, the soft consists possibly of several subdiagrams that are connected, but they have to be connected to at least 2 jets, sometimes more than 2 jets. Okay, so this is the theorem, and for the proof, Yao is here. I'm sure he would be happy to discuss that. Okay, now the third level of understanding this expansion is to say the following. Okay, we have a general classification of how the regions should look like, shown here. Very good, but look at the diagram. Can you tell me what the regions are? And the answer is yes. It's actually very simple rules that one can formulate, which we have proven that they are, basically they follow from the theorem, that one can look at a given diagram and just find all the regions in a very simple graph theoretical way. So here we see an illustration of that for this fishnet type diagram. The stage one is come up with a candidate jet subgraph for each of the particles that are getting on shell. So here we came up with this. Basically, the idea is that you take a unitarity cut, separating between this leg getting on shell and the others, and the propagators that are cut are the ones that are the last ones that are part of this jet. And then you do the same for all the jets, all the external particles that are getting on shell. And then you overlay these diagrams, and you get this. What does it mean, this overlay operation? We basically count to how many jets each edge belongs. If it belongs to just one jet, then it would remain part of this jet. If it belongs to two or more, like this propagator here, it's part of this one and this one, then it would be soft. And if it is part of no jet, like this one at the bottom here, then it would remain hard. So that's very simple rules. So that's the algorithm to just look at the diagram and determine the regions. That works for any loop order, and it gives you the regions to any power. Okay, so now we come to the central part of the talk, and that is what happens beyond facets. So far, we had an algorithm to find the regions, but in the small letters, there was that this is really an algorithm when the signs of the monomials are always the same. But clearly, the signs of the monomials are not always the same. So we will need to think a little bit beyond the facets. And well, I have to say that this has been investigated in the past, but basically, all the examples that have been given where this geometric approach was failing were either in the threshold limit or in the forward limit. So there are very specific exceptional kinematics. And the question that we would like to address, does this happen for general kinematics? Does it happen for massless scattering at wide angles? Then it would, you don't have to go to any special limit. Is this indeed a problem also for such an expansion? And, well, we will see. But basically, in order to answer this question, we have to do something more fundamental. We have to return to the Landau conditions and see, first of all, whether there are Landau singularities that can induce such a region. Because all these regions are related to the proximity of some Landau singularity. Now, when we look at this equation here, we realize that there are two types of solutions. There are endpoint solutions, and there are pinch singularities that are away from the endpoint. The whole business with this geometric approach, where we scale the integration variables together with the external, is based on the idea that these are endpoint singularities. We scale alphas to 0, okay? Now, that's not generally the solution. I mean, there can be situations where there is a solution to this equation away from the endpoint. So let's see when this happens. So we had to come up with a criterion for what we call class B. How can we identify, looking at the diagram, a situation where we have class B? Now, of course, we could solve the Landau equations, look at the solution of the Landau equations and say, well, declare that whenever we find a solution with a variety different that is not at the end point of the integration domain, then we declare that. But we wanted to have a quick way to brush through all the class of diagrams, even ones where we cannot solve the Landau conditions for. And then we devised this cancellation requirement that allows for a simple algorithm to set up to scan through the diagrams. What's the idea? The idea is that you write the F polynomial as a sum of positive and negative monomials. Then the Landau conditions take the following form, right? It's the derivative of both these monomials and these monomials. And the cancellation requirement to have this type of solution is that there exists at least one alpha I, such that df plus to the alpha is not 0, df minus to the alpha is not 0, but their sum conspires to be 0 on the solution. So they are really they really cancel due to the fact that there are different signs, rather than due to some alphas going to 0. Okay, so now I show you the full algorithm, but due to lack of time, I'll not go line by line through the algorithm. Basically, we devised an algorithm that is easiest to apply when we look at kinematically independent Landau singularities. So we are looking for situations, precisely like in David's talk, we are looking for a situation where there is a Landau singularity for any assignment of the external momentum, okay? And that's basically this formulation of this algorithm. And then we applied it to 2-to-2 diagrams. We were able to then run it through all 3-loop and 4-loop graphs. I'll not discuss much of it, but I'll discuss the 3-loop situation. So basically, at 1 and 2 loops, we show that all the diagrams, okay, thanks. All the diagrams basically are in the category that there are only endpoint singularities. There are no such pinch singularities, so no problem. Expansion by region is supposed to work with this facets of the Newton polytope. That's the full story. At 3 loops, on the other hand, there are 10 non-planar topologies that have such a singularity. And these are the topologies. So these are this is what the algorithm gives us. These are the 10 suspicious guys that can have a cancellation solution of the Landau equations away from the endpoint. You see that all of them contain this diagram plus some extra propagators. So basically, if we understand this one, we understand the story. Okay. By the way, the same happens at 4 loops. All the diagrams at 4 loops that have such a problem, they contain these guys inside. Okay. We'll not go to 4 loops in this discussion. Just want to take the simplest example where this thing occurs and understand it to the end. Okay, so here I wrote this integral in the Feynman parameter representation. Notice that I look at it exactly on shell. So I put the externals on shell. I'm interested in expanding about the on-shell limit. The relevant Landau singularities would be the ones strictly on shell, not for the off-shell situation. So this is very simple, because the F polynomial has only these terms here. And you don't need any computer to realize that this has solutions such that the derivatives of F would all vanish on the solution due to the cancellation between positive and negative monomials. How can you see that? Okay, let's take the derivative of F with respect to alpha 1. Then you see it would be proportional to that in as far as the S12 term is concerned. And remember, we don't care about what the other one is for this. So the derivative with respect to alpha 1 should vanish independently for S12. So this thing has to vanish. This combination here in the brackets has to vanish on the solution. But clearly it can, because these alphas are positive and there is a negative sign here. So upon choosing a specific ratio between them, that can vanish. So basically, if you look at it, the solution requires that all 4 of these, we need all derivatives to vanish, all 4 of these vanish simultaneously. An example is when all the alphas are 1/8, then it's very easy to see that this vanishes and all the derivatives vanish. Okay, very good. So we have a pinch singularity. Now the question is, does this lead to a region in the on-shell expansion? The answer is yes, that's the region. Here we use coloring to indicate each propagator, how it scales. So basically, the green colors here indicate that these are jet propagators, or collinear propagators to the external line. So each pair is collinear to the adjacent external line. That's this description of the region. So they're all jet-like. But the special thing is there are 2 hard connected points of interaction. Separate, disconnected, hard, right? Because there are 2 points of interaction. And that is a clear departure from what we have shown, what we have previously shown for all facet regions. All facet regions have a single connected hard subdiagram. Here there is a departure. So clearly, such a region, if it exists, I've not yet shown you, if it exists, then it would be something on top of the facet region property that we identified before. Let me try to guide you through the logic of how we see that there is indeed a region. So first of all, we go to the Lipomeranski polynomial, and then this solution where we have some finite value of alpha, like 1/8, has to be consistent with this relation between the x's. That means that all the x's should scale with lambda in the same way. Otherwise, we are not going to get a finite number here. So it should be something like, they scale like lambda to the minus n, where n is the same for all of the edges, okay? But because these are jet, because these are external light-like particles in the limit, we know that they are supposed to be jet momenta, collinear momenta, and therefore the natural guess would be that they are all -1. Now, let's try to take this sort of region vector in quotation marks and substitute it into the polynomial, this scaling. Well, we will find something very awkward. What we will find is that these two terms in the F polynomial, they would scale like lambda to the -4 based on the degree of homogeneity, simply. And all the other terms scale like lambda to the -3. So we will not get a region from that. This would integrate to 0. There is no enough monomials to give a non-vanishing integral. It's a scaleless integral. But clearly, we miss something important here. We miss the fact, this is the naive counting of the monomial scaling. Clearly, what is important here is this minus sign. How can it be taken into account? Now, the point is that on the solution, these had to vanish, right? So that means that they are getting small. The ratio, their difference is small compared to the absolute value of each of them. Okay? And so if we require that each of these factors is square root times the naive value of each of them, so scale like square root, then these together scale like lambda to power 1, and then you get that this entire F polynomial scale like lambda to the -3, the same as the U polynomial, and you get a region. You get something that is scaleful, that actually does not integrate to 0. So the requirement is that the relation between the x's behaves like that. Okay, despite the fact that they scale to infinity while preserving this relation here. Clearly, this could not be found by facets of the Newton polytope that completely ignore the coefficients in front of the terms. Remember, the facets of the Newton polytope, they know only about the power behavior of each of the x's in the monomials. They don't know about the signs in front. So we have detected a region that is missed by this algorithm. How to actually expose that in a more algorithmic way, because here I was guided by some intuition. There is a way to do that. Once we know what the Landau singularity is, then we can rescale the kinematic variable, the Lipomeranski variables in an appropriate way, such as to linearize these factors. And you see, then we get this polynomial. Then it's very clear that these y's that are of order 1 have to cancel between them, precisely as the square root of lambda that are indicated, and then get this result to be scaling like lambda to the -3. So now the next step is to break the integration domain such a way that each of these factors has a constant sign. So we have to break it depending on the hierarchy of these 4 y's. So this amounts to 4 factorial. We have to break it into 24 parts, and that corresponds to dissecting the polytope. What are we actually doing here? We discovered that in this polytope, there is a singularity lying inside. We are changing variables so as to linearize it, and then we just cut the integration domain at the singularity. Now, we will have the singularity lying on the separation. So it will be, again, an endpoint singularity. Once it's an endpoint singularity, we can apply the same tools we applied all the time, because then it's facet, and it would be detected. And let me show you that it is indeed detected. This is the original polytope. The original polytope has 6 facets here, and none of them is power divergent. You see that they don't contain this -1, -1, -1. Of course, it's not there. It's not a facet. But Here I give you an example of one of these 24 dissection of the polytope in the new variables and then translated back to the old variables. Suddenly you see that there is this -1 and there is this -1 occurring again with a factor of 2. That's the same vector essentially, not the normalization here. Basically, this factor, this vector here appears due to the new separation that is now a facet of the polytope. And this is the power, this is a power divergent region. So basically what the original formulation missed is the most important region, the only region which is power divergent. So it's an extreme example where it doesn't only miss, it misses the only important contribution. Here there is a numerical check, so these integrals are not yet known analytically, so we had to devise a method to integrate it numerically, and here you see the result of the numerical integration in blue for the full integral compared to the evaluation of the leading region, and you see that, that they coincide if P1 squared is small enough. So this is a numerical illustration that indeed it captures the divergent behavior. Once we have determined the situation, the facet regions of this diagram here, then it is fairly straightforward to determine the region structure for all the diagrams here. It is really the same underlying structure. So basically, these are all of the hidden regions that you find for 2-to-2 scattering for 4-point functions at 3 loops. There is nothing else. These are the complete set of hidden regions that you need to supplement to the Newton polytope analysis with. What is the interpretation? This is the interpretation that we now have as a theorem for the structure of regions in the facet category. So these are the ones that come out of facets. The conjecture is that the only type of regions that appear beyond the facet picture, namely due to these hidden regions, are of this kind. And we call them Landau because Landau was the one that introduced an analysis of multiple hard scattering. So the conjecture is that the only thing that's missing are these that involve multiple hard scattering processes. And actually, it's the same modes that appear as in the original case. So no new modes. That would be that's quite important for soft collinear effective theory. If there were new modes, it would be great, but somehow sad news. So far, this is not detected. Okay, just a couple of slides to briefly show you what happens in the Regge limit. In the Regge limit, we now take everything on shell, and we just consider T much smaller than S. It's very simple. But the region structure is not simple at all. There are several new modes that appear that did not appear in the on-shell expansion. Let's see what happens to these regions that were hidden in the case of wide-angle scattering. Of course, there are also hidden regions in this case. It's even easier in general to find such regions because there is half the number of Landau equations that have to be satisfied. In this case, the physical interpretation is different. These become Glauber modes that propagate. So one of the loops is going to be a Glauber loop, and the other are collinear loops. That's the analysis of the hidden regions in the Regge limit. At 3 loops, there is nothing beyond that. At 4 loops, there is. Okay, so that's it. Now let me summarize the conclusions. I'm sorry for going a little bit over time. So first of all, I showed you that in the parametric representation, Landau singularities are typically endpoint singularities. So being endpoint singularities, they are subject to these tools, the geometric interpretation, and by looking at the Newton polytope, we get out almost a complete set of regions. We get out a lot. If all the singularities were endpoint, this is the end of the story. However, the signs in the F polynomials are eventually important, and at some point it hits us, and it hits us even in the case of wide-angle scattering. In case of wide-angle scattering, we now have, at least for 2-to-2, we have some mapping of what's going on. We know that we established that there are only hard collinear and soft modes in the context of facet regions, and we see that actually the same modes appear in the context outside of facet regions for these hidden regions. And we have this conjecture that this is the only generalization that one needs to make going from the facet regions to the hidden ones that seem to be consistent with all the evidence available, but this is only a conjecture. Okay, so then there is a very interesting analysis that's ongoing about the high energy limit, where there are Glauber regions, and that feeds into some extra analysis of the high energy limit from other perspectives. Okay, so I'll stop here for questions. Thank you very much.
Are there any questions?
So in the Landau example that you've been telling us about, when you cut the region into these 4 factorial regions, where in each region, the singularity is on the boundary of each region, is it in a facet? Is it in what dimension?
Yeah, so sorry, this was a bit quick. Indeed here, so this is a facet analysis of one of these 24 parts. So the fact that this is detected by bisectec, this is a bisectec output, it is detected in these variables as a facet, and this is the region vector normal to that facet.
Yeah, fantastic.
So yeah, so it is indeed a facet, and it just, so basically the same tools, once you have dissected the right point, that's it.
And do you have any freedom? The dissection seems to be kind of forced on you in this example. Yes. You have no choice, right? There's just one.
Yeah.
Is that the general story, do you think?
Well, we have not encountered a case where there's a more complicated structure of this hidden singularity. What I believe happens in other expansions, or when you have more legs, is that you'd have also Landau singularities that do depend on the invariants, on the ratios between invariants, of course. And some of them, of course, there are many Landau singularities. The important thing is that some of them appear within the domain of integration, and then they would actually induce regions. So that's the general picture. So the general picture is much more complicated. So here we could analyze it very cleanly because we restricted ourselves to the on-shell expansion and to a low number of legs. But generally, the situation is more complicated.
Anyone else? All right, let's thank Einan again.
Okay. Thank you.
And just add my thanks to the organizers for the week and for the workshop to come.